Hi guys. Hope you're feeling good. Today in O-Level Physics, Lesson 8, Particle Model and Thermal Properties. The kinetic particle model describes solids, liquids, and gases. Solid particles vibrate around fixed positions and are closely packed. Liquid particles remain close but move past one another. Gas particles are far apart and move randomly. This model explains shape, flow, compression, and diffusion. Diagrams should show arrangement and motion, not different-sized particles for different states. Temperature indicates the thermal state and is linked to average random kinetic energy of particles. Internal energy is the total microscopic kinetic and potential energy of particles. Heating transfers energy because of a temperature difference. During a temperature rise, average kinetic energy increases. During a change of state, energy mainly changes particle potential energy as attractions are overcome or formed. Specific heat capacity C is energy required to raise the temperature of 1 kg by 1 degree C. E equals mc delta T. Heating 2.0 kg of water by 15 degrees Celsius, with C equals 4,200 J, kilograms degree C, needs 126,000 J. A high C means more energy is needed for the same mass and temperature rise, helping oceans moderate coastal temperatures. Melting and boiling occur at fixed temperatures for a pure substance at constant pressure. During the plateau of a heating curve, temperature remains constant even though energy enters, because particles separate rather than gain average kinetic energy. Specific latent heat L gives E equals mL. Evaporation differs from boiling. It occurs at the surface at any temperature and its fastest particles escape, cooling the remaining liquid. Gas pressure results from particle collisions with walls. Heating a sealed rigid container raises particle average speed, so collisions are more frequent and involve greater momentum change. Pressure rises. Compressing at constant temperature shortens travel between walls, increasing collision frequency. A complete particle explanation links a change in motion or spacing to collision rate and force, rather than merely saying particles expand. Thermal expansion occurs because average particle separation increases when a material is heated. Particles themselves do not grow. Solids expand least, gases most. Expansion is useful in liquid thermometers and bimetallic thermostats, but bridge joints and overhead wires need allowance. When mass is constant and volume increases, density generally decreases. Cooling reverses the trend, with water near freezing as an important exception. Identify whether temperature changes or state changes. Use E equals mc delta T for a sloping heating curve section and E equals mL for a plateau, with mass in kilograms and energy in joules. A 0.50 kg metal of C equals 400 J, kilograms degree C, warms by 30 degrees Celsius. E equals 0.50 x 400 x 30 equals 6,000 J. No latent heat equation is needed because its state does not change. Do not say heat is temperature, claim particles expand, use E equals mc delta T during a phase change plateau, or describe evaporation as happening throughout the liquid at one fixed temperature. Practice. Find energy to heat 0.80 kg of material with C equals 500 J, kilograms degree C, by 25 degrees Celsius. Answer: E equals 0.80 x 500 x 25 equals 10,000 J. Watch the numbers land in the matching symbols. Check that units cancel cleanly. If they do not, the setup is wrong even before the arithmetic. Practice. A 0.20 kg solid melts with L equals 150,000 J over kilograms. Find energy and explain why temperature is constant. Answer: E equals 30,000 J. Energy overcomes particle attractions, so average kinetic energy and temperature do not rise. Watch the numbers land in the matching symbols. Check that units cancel cleanly. If they do not, the setup is wrong even before the arithmetic. Alright, that wraps up particle model and thermal properties. Next lesson we'll move on to thermal energy transfer. Hope that helped. Catch you next time.